Okay, so the next thing that we'll need to know is the conditional probability rule. Here's the formula. Now, whenever you see this notation, the probability of A given B, that would indicate a conditional probability. The condition is that you're given some information in the problem. You want to take the probability of A and B divided by the probability of B. Whatever event you're given, that's going to be the probability of the event that you're going to be dividing by. So there is an order to how we're writing this. Now, what I have written over here is really just kind of a calculation to show you that this formula is not really a new formula. It just kind of comes from a little bit of algebra on the multiplication rule. Now, sometimes when we work with these problems, we might have a table, like the one that is in problem 25 in your notes. If you were to flip to that, there's a table there. And so in the probability calculation, we're really not going to be computing probabilities until the very end, which means that I'm just going to be using the number sign instead of the probability sign. We'll look at an example of that later. Problem 37, let A and B be two events with the probability of A equaling 0.3 and the probability of B equaling 0.4, and the probability of A and B equaling 0.2. What is the probability of A given B? Okay, so whenever we have a conditional probability, I would say go right to the formula. Here it is. And the probability of A and B is 0.2. That was given to us here. And the probability of B is 0.4. That was also given. 0.2 divided by 0.4 is 0.5. Part B, what is the probability of B given A? Well, here I've just switched the two events. So where I see A, I'll write B, and where I see B, I'll write A, using the formula. Okay, now the probability of B and A, that's the same as the probability of A and B, right? If I switch the events, I'm still talking about the same overlapping region on the Venn diagram. And means I'm shading the overlap, so that probability would be 0.2. The probability of A is 0.3, and I would get 0.6 repeated in this answer. Part C, does the order of the events matter when writing a conditional probability? They don't matter when the keyword is and, like we see here, we still get 0.2 if we switch the events. They do matter, though, in the case of a conditional probability. If you switch the events, you're not going to get the same result necessarily. Okay, so there is an order to what we're doing there with the notation. Part D, are A and B independent? There's a couple of different ways that we can conclude that the answer is no. Remember that independent events mean that the occurrence of one event does not affect the probability of another event. So just because you're given event B, that wouldn't matter in finding the probability of A since you get the same number. Now here we don't see that, because the probability of A given B is 0.5, the probability of A is 0.3. Those are not the same number, which is why we're concluding no. Here's some other options that you can conclude why the answer might be no. The probability of B given A, which we found, is not the same as the probability of B. Also, now here's the multiplication rule for independent events. I mentioned that you can only use this formula if A and B are independent. If A and B are not independent, we can't use this formula. If you were to take 0.3 times 0.4, you would not get 0.2. Okay, so either way that you look at it, these two sides aren't going to produce the same number. Problem 38 is another example. It says, suppose that one card is randomly selected from a 52-card deck. Let E be the event that you draw an ace, and F be the event that you draw a club. Part A, what is the probability of E? Well, there's 4 aces in a deck, 52 cards. 4 over 52 is 1 over 13. Nothing new with there, that's just a basic probability. Part B, what is the probability of E given F? Okay, here's our conditional probability again. So I, again, say go right to the formula. We need the probability of E and F divided by the probability of F. Since I'm given event F, I want to be dividing by the probability of that event in the formula. E is the event that you draw an ace, F is the event that you draw a club. If you want the card to be an ace and a club, there's only one of those, that'd be the ace of clubs. So 1 over 52 would be the probability of getting the ace of clubs. The probability of F, well, F is the event that we draw a club. There's 13 clubs in a deck, so 13 over 52 would be the probability that you get a club. You're dividing by a fraction, so the rule would be to flip the denominator. That way the 52s would cancel, and going to leave you with 1 over 13 then as the answer. Now in this problem, what we're saying is that we don't have all 52 cards in front of us. And by the way, that would be the condition in a conditional probability, is that your sample space is reduced in size. For this problem here, I've only got 13 cards in front of me. I'm given the clubs. Okay, so if I'm only given those 13 cards, what is the probability that I select an ace? Well, only one of those clubs is going to be an ace. So 1 over 13, like I could have went right to the answer in that had I just thought about the problem. And again, that in general is going to be the case when you have a conditional probability. The condition is that your sample space is reduced in size. Part C, are E and F independent? So I'm using the definition for independent events. The probability of E given F was 1 over 13, and that's also the same as the probability of E. So in this problem here, like, it's not going to matter how you look at the calculation. You could have all 52 cards in front of you, and you have a 1 over 13 probability of getting an ace, or you could only have 13 clubs in front of you, and there's still a 1 over 13 probability of getting an ace. Either way that you look at it, you get 1 over 13 as the answer. Now, they're not asking for it in this problem, but if they were asking for if E and F are mutually exclusive, then the answer to that would be no, since you can have a card that is an ace and a club, right? There's one of those that we just said. Mutually exclusive events means that the two events cannot occur at the same time. Again, don't get that term confused with independent events, where it's two totally different things there. So yes, these are independent. No, they are not mutually exclusive. Problem 39, according to the U.S. Census Bureau, 19.1% of U.S. households are in the Northeast. In addition, 4.4% of U.S. households earn $75,000 or more per year and are located in the Northeast. Determine the probability that a randomly selected U.S. household earns $75,000 or year or more per year, given that the household is located in the Northeast. Okay, given is a key word there, and that tells me that I'm going to have to use a conditional probability. In this problem, I am not looking at all the households in the United States. I am only looking at those in the northeast region of the United States, so I must indicate that when I set this up. So given that condition, what are the chances that I select a household that earns $75,000 or more? Well, I'm using the conditional probability rule, and the probability that somebody earns $75,000 or more and is located in the Northeast region, they told us that was 4.4%. Here's that number in decimal form. Okay, 19.1% of households are in the Northeast, so 0.191 would go in the denominator, and you get roughly 0.2304. Okay, so again, the thing that I want to emphasize here is that in this problem, we are not looking at all the households in the United States. Okay, like it would be important to indicate the condition. We're only looking at those that are in the Northeast region, and if we're only looking in that region and we select one house from that region, there's a 23.04% chance that the household would earn $75,000 or more in a year. Problem 40. The following data represent the passengers who survived or died for the ill-fated Titanic voyage by gender. The males are adult males and the females are adult females. Okay, so there's three groups: male, female, and child. Here's our table of information. Part A, what is the probability that a randomly selected passenger who was on the Titanic was female? Okay, so there were 2,224 individuals on the Titanic. 424 of them were females. When you divide those two numbers, it looks like there's roughly about a 19.1% chance that the individual would be a female if it were a random selection. Again, nothing new there, that's just a basic probability. Part B, if a female passenger who was on the Titanic is selected at random, what is the probability that she survived? Okay, now they're not saying the word given in the wording here. However, we would still want to recognize that we have a conditional probability. We're not working with all those that were aboard the Titanic. We're only working with the female passengers. So if we're given that group, what is the probability that we select a person that survived? Here's my setup here. Again, this is a conditional probability. Now, because there's a table in this problem, and I'm going to get row totals and column totals, like my probability is really not going to come until the very end. So I'm still using the conditional probability formulas, just instead of the probability sign, I'm using number signs. We want the number that would be in A and B, okay, survived and female. That would be 316 when you match up that row and column. Divided by the number of females, that would be 425. Okay, so there's roughly about a 74.4% chance of the person surviving if we know that the person was a female. Part C, if the passenger who survived the Titanic is selected at random, what is the probability that this person was female? Okay, so again, we're not working with everybody on board the Titanic. We're only working with those who survived. And given that group of individuals, if we pick one, what is the probability that the person is a female? Since this is a conditional probability, use the conditional probability rule. Again, I'm using the number sign here. And the number of people that were female and survived would be 316. Again, when the keyword is and, the order is not going to matter. Okay, so you can have those flipped. Divided by the number that survived, there were 711 that survived, and so 0.4 repeated is what would be the answer. So if we're only looking at the group that survived and we pick one, there's about a 44.4% chance that the person was a female. Part D, are the events female passenger and passenger who survived independent? No, since if you look at the probability of selecting a female given the fact that that person survived, that number is not the same as the probability of selecting a female. Those are different numbers, and therefore the answer is no. Part C in this, if a child passenger who was on the Titanic is selected at random, what is the probability that the child survived? Okay, so we're only working with the children now, and we're going to pick one of them. We want to find the probability that the child survived. This is a conditional probability rule, and if you match up the top row and the third column, 57 people were children and they survived. There were 109 children on the Titanic, and so when you divide, it looks like we get roughly about a 52.3% chance that the person survived if we know that the person was a child. Part F, if a male passenger who was on the Titanic is selected at random, what is the probability that he survived? Again, this is a conditional probability. There were 338 males that survived, and there were 1,690 males on board. So when you divide, you'd actually get 0.2 exactly. Okay, so if we only had the group of males and we pick one, there is a 20% chance that that male survived. Part G, compare your answers to parts B, E, and F. Do you think that the adage "women and children first" was adhered to on the Titanic? Yeah, what they want you to see here is that the survival rate was much higher for women and children. If you look at the conditional probabilities, there's a little bit less than a 75% chance that the person survived if we know that the person was a female. you have more than a 50% chance that the person survived if you know that the person was a child. But you only have a 20% chance that the person survived if you know that the person was a male. Okay, so yeah, I buy the fact that they were using that that plan, women and children first. Now, there were significantly more males on board, but when you look at the conditional probabilities, the survival rates were higher for women and children. Here's the homework problems for section 5.3 and 5.4. Be sure to look at those when you get the time to.